Today we'll talk about inductors. You learned that. Do you guys remember what capacitors do?
They store a voltage potential across two plates.
Yeah, so they store energy, and they store energy in the form of electric fields that they create. And when they're charged, there's an electric field in between them, and they store energy in the form of electric field. You learn inductors will store energy in the form of magnetic fields. Okay? So that's one of the things they do. And between capacitors and inductors, you can make tuning circuits, which is at the heart of all wireless devices. So we'll talk about that second half, okay? So this chapter is based on this equation. Okay? What does this equation tell you? That changing magnetic fields, time-varying magnetic fields, will induce electric fields. Okay? So let's see if you remember stuff from a previous chapter. Let's say I have a magnet, and what you want to do is change the magnetic field with respect to time at some spatial point. Okay, so let's say I want to increase the magnetic field at this point. What will I do to increase the magnetic field in that region? What can I do? Move the magnet up. If I move the magnet up, the magnetic field will increase here. And if I move it down, the magnetic field will decrease. Okay? So that's how we'll change the magnetic field. All right, so what this equation tells you is if the magnetic field increases in this direction, Mr. Lenz says that you will induce a field such that you will induce an electric field in this direction such that this produces an opposing magnetic field. Okay. So anyway, a changing magnetic field induces this electric field, and if you stick a wire there, it'll pass a current through this wire. Okay. So changing magnetic fields is what induces the electric field. Now is there another way to change this electric field? This magnetic field. So let me show you another way. Okay, I'm going to pass a current through this loop of wire. What does this act like? This will produce a magnetic field like so. Okay. So what is my goal? To change this magnetic field. How can I change this magnetic field?
You change the current.
There you go. Okay. So I'll change this current. I'll make this current time dependent. Okay, and the easiest way to do that is to plug that wire into the wall. Send an AC current through this. And this magnetic field changes all the time. Okay? And what that'll do is, if I have a second loop here, it will induce a current in this loop, and the direction will switch back and forth. And that's what this chapter is. Okay? A lot of applications on this chapter are about that. Okay. Now let me ask you this. If I move this loop closer, will the induced current be higher?
Yes.
Yes. And that makes sense. If it's very far away, it doesn't even see the magnetic field. Okay? So the induced current will be higher. If I put more loops in the secondary coil, will that induced current be higher? Okay, and so on. Okay, so that's the application. We'll see. Okay, so everything is based on this chapter: changing magnetic fields, producing electric fields. So here we go. So here is a coil. I'm going to feed an AC current through this coil, and the current is producing this magnetic field. If I pass an AC current through this coil, this magnetic field changes and it induces a current in this coil. What happens if I pass a DC current through this coil?
Magnetic field is constant.
Mhm. And there won't be any induced EMF in here. Okay, so what we want is a change in currents fed in here that'll induce a voltage there. Okay. Now, the most important application of this phenomenon is mutual inductance. This is called mutual inductance. You're inducing a current in the secondary coil by a change in current in the primary coil. Okay, so this is a phenomenon of mutual inductance, and the most important application is in transformers. Okay, and I'll talk to you about induction stoves and wireless charging. Okay, so now let's look at the equation, important equation. Okay, so what this equation tells you is the EMF induced in the secondary coil, the voltage induced in the secondary coil due to a changing current in the primary coil. All right, so you're inducing a voltage in this coil by changing the current in this coil. And that proportionality constant is called the mutual inductance. All right, so let me ask you a couple of questions. All right, so if I move this guy further out, what will happen to the voltage induced in there? It's going to drop. So that means this constant is going to drop. It's going to get smaller. Okay. What if if this secondary loop was like that instead of like this? What would happen to the voltage? Any voltage. Okay, so this would go to 0. Okay, so you see this mutual inductance depends on the configuration of the two loops, distance between the two loops, and so on. Okay, so that's why in general we can't give you a formula for this. Okay, it'll depend on the configuration of the two circuits. Okay? The stronger the coupling, the bigger this number is. Okay, this is called the mutual inductance, and that is telling you how much EMF is induced in the secondary coil due to changes in current in the primary coil. Okay. All right, so that's the whole chapter about, and so let's do a couple of applications. Have you guys heard of induction stoves? Does anybody have induction stoves?
Are those the ones with just the metal coils that physically heat up?
No. That's just an electric stove.
They don't even touch the pan.
I have one electric.
Do you guys have one?
induction
No.
cooktop,
Mm.
and it just creates a magnetic
You can
field.
basically have it in a countertop.
That's
Yep.
hot.
Mm-hmm.
That's what it is.
All right, so what did we learn? You feed an AC current through here, and it will induce a current here. Okay, it'll induce a EMF there or a current there. So here's the idea. Here's a coil, and you feed an AC current to this coil. This will produce a magnetic field, and if you feed AC current through it, this magnetic field changes. Right now it's like that, and the next half cycle it will be pointing up, down, and up. Okay? And now if you have a metal pan, what is a metal pan? It's a good conductor. This changing magnetic field will induce an electric field, which will drive a current in the metal pan. And what happens to the current in the metal pan? The metal pan has resistance, and that current gets turned into heat. That electrical energy gets turned into heat. So that's how, through induction, you're heating this pan. This thing won't get hot at all. Yeah? It'll be easy to clean. This is the most efficient stove. An induction stove is about 90% efficient. A gas stove is 40% efficient. Electrical coil, you can just heat a coil and set your pan on top of there, and you're wasting a bunch of heat here and there. Okay? So the electrical coil is about 70% efficient. And these are fairly common, electric radiant. You have an electric coil underneath, a ceramic plate on top, so that's just for cleanliness and stuff. And then you put your pan on top. So here's an electric coil that gets hot, a ceramic plate, and then this is what I have at home. And energy is getting through conduction and radiation. Okay? So that's about 10% less efficient. Okay, so induction coils, these stoves are the most expensive, but they're the most efficient. Okay. You've heard of wireless charging. You guys probably all use them. Okay. So again, what is it that you need? You need a primary coil. You feed AC voltage to it. Okay. And this will produce a magnetic field that's switching back and forth. And you have another coil here. So this changing magnetic field will induce a current in that, AC current in that secondary coil. Okay? And then you take that AC current and pass it through a rectifier and convert AC to DC. We'll talk about a rectifier in the next chapter. Okay. Hold up your block.
A what?
Your block, your brick. Yeah, so that's a rectifier. That's what its job is, to convert AC to DC. Okay. So that's how wireless charging works. Okay, you can do that for cars as well. Okay. Wireless charging efficiency is the high-end efficiency is about 90%. Okay. And wired charging is about 95%. So, okay. It turns out that with wireless charging, so why would you wirelessly charge if the efficiency is lower?
Convenience?
Convenience, and also it turns out that you need fewer components in the cars. Some of those components can be put here. So if you have wireless charging for multiple cars, you can have, so if every car was going to.
It's better for like a fleet of vehicles.
Right.
Okay.
But I guess Tesla probably won't install those wireless chargers in the. I mean, you just have to do a cost-benefit analysis. How much are you saving by having fewer components? Yeah. And if the charging efficiency gets to be comparable, then, that's the way to go. All right, so again, everything we talked about depended on this phenomenon. You feed an AC current through this coil, and you're inducing a current in this coil through the coupling. Okay? And that's what transformers do. So we'll talk about transformers. Yeah, there's the slide on transformers. So you feed an AC current through this loop, a wire, and this magnetic material, what it does is it's taking all the magnetic field produced here and passing it through this. So it's directing this magnetic field through there. Okay? And so as the current changes, the magnetic field through this thing changes, and it induces an EMF there. Okay, induces a voltage there. And it turns out that, so like I said, the voltage will depend on the number of coils and all that. So the amplitude of the voltage in the secondary coil is equal to N2, the number of turns there, divided by N1, the number of turns here, times this voltage, V1. So so again, what do you have to do? You have to feed an AC voltage, and what you get out is an AC voltage. So, so this would be a transformer. If N2 is greater than N1, then it's called a step-up transformer. the amplitude of the output voltage is greater than the amplitude of the input voltage. What if N1 is smaller than N2 is smaller than N1?
Step down.
Step down. All right, so let's look at this. Let's say we have an amplitude of 1 volt, and N2 is 1,000 times greater than N1. The amplitude of the output voltage is 1,000 volts. We've said 1,000,000 times there's no free lunch, but looks like we finally have arrived at free lunch. Okay, what's going on then?
I don't know how it works, but I think it's called impedance.
What then?
Impedance?
So here, power output, power input equal to power out. And power is voltage times current, voltage times current, okay? So if you increase the output voltage, you're decreasing the output current, okay? And of course, we use these things all the time. So here's Hoover Dam. You step up the voltage in several stages to 800,000 volts. So transmission losses are minimized, and then step it down in several stages to 240 volts. And that comes to your house. Okay, 120. So, all right, so we are using mutual inductance in several applications. Again, mutual inductance is, okay, you're inducing EMF in a close by coil by changing the current in the nearby coil. All right, so we saw all of that. So the induced EMF in the secondary coil depends on the rate of change of current in the primary coil. And this constant depends on how strong the coupling is. This mutual inductance tells you how strong the coupling is between the two. Okay. You guys understand all of that? Yeah. All right. All right, so now let's do the following. Yeah, so here's a funny thing. All right, let's take a straight wire. And this is just for illustrative purposes. What I'm going to do is, so I'm connecting a voltage battery to it, and I'm going to crank up the voltage on the battery. You guys have done this in lab. And you know, what will happen to the current?
It's going to increase.
It's going to increase. Okay? And the response will be instantaneous. Okay? Now, what I'm going to do is, I'm going to take this straight wire and I'm going to wind it into a coil. I'm going to wind it like this. So let's see what will happen. Okay, let's see. Okay. So this coil is going around like that and so on. Okay. Now I'm going to pass a current through this coil. Okay. So what is this first coil going to do? This current passing through the first loop going to do?
It's going to generate a magnetic field.
It's going to generate a magnetic field, and you guys all agree that the magnetic field will be in this direction. Okay. Stick your fingers in the direction of the current and your thumb points in with your right hand. Okay. And this will generate a magnetic field there. Again, what I'm going to do is, now, see, if I increase the voltage here, the current increased without any problem. Now I took this wire, I folded it into a loop, and now I'm going to try and increase the current here. Let's see what happens. Okay, this magnetic field will increase. That magnetic field is coupled to the second loop. That's going to fight this increase. It doesn't like it. It's going to produce a magnetic field in the opposite direction. It is going to induce a current in the opposite direction. It's going to induce an EMF in the opposite direction. Okay. Oops. Okay. This current that was supposed to go in this direction, you're trying to increase it, and an EMF is induced in the opposite direction. So what we're saying is, you took this straight wire, as long as the wire was straight, you could increase the current and it wouldn't protest. You took the same wire, wound it into a loop, and suddenly it doesn't like you increasing the current in it. Okay? So if you try and increase the current, it'll produce an EMF in the opposite direction, fighting the increase in current. Okay? If you try to decrease the current, it'll produce an EMF such that it wants to maintain that current. It doesn't want any changes in current. Okay? This device is called an inductor, okay? And we'll measure its self-inductance. How hard does it fight the change in currents? Okay. So you can see that you connect a device like this to an AC source, you'll have a fight back. Okay. So an opposing self-induced EMF develops as current increases or decreases in an inductor. Okay. The self-induced EMF is proportional to time rate of change of current in the inductor. Okay. So if the wire were straight, I close the switch at time t equal to 0, the current will go from 0 to its steady state value. Okay. If I take this wire and wind it up into a thing like that, now the current will rise exponentially. It'll still get to the same final value, but the behavior of that coil has changed. Okay. All right, so here's a coil. If I try and increase, I took that straight wire and then wound it up into a wire. If I try and increase the current, it produces an opposing voltage. And if I try and decrease the current, it'll produce a voltage such that it tries to maintain that current. Okay? So you took the straight wire and wound it into a solenoid, and what happened? Now it doesn't like currents changing. It'll fight. If a current is changing, it'll fight that. If a current is trying to increase, it'll try and fight that, and if its current is trying to decrease, it'll fight that. Okay, so the induced EMF, this EMF that this coil produces, the induced EMF, again, is proportional to the rate of change of current, just like in the previous case. Okay? Mutual inductance was between two separate circuits. Self-inductance is within the circuit. Okay? But they're both proportional to time rate of change of currents. Okay? So the induced EMF is proportional to the time rate of change of current, and this proportionality constant is called the inductance. Okay. The negative sign just telling you that the induced EMF is in the opposite direction of the increase in current.
The unit is the Henry.
And the unit is a Henry. Well, all units are named after people, so Mr. Henry did work on this stuff. All right. So if you take a wire and closely wind it, and it's air filled, the inductance of such a coil is mu naught. Mu naught is the permeability of free space. N is the number of turns per unit length. And A times L. A is the area of cross section, and L is the length of the inductor. So that's the volume of the inductor. So here we were able to give you a formula for the inductance. Okay? because we've already told you the configuration of this thing, okay? Remember, for mutual inductance, it depended on the configuration of the two coils and the location of the two coils, so that was harder to give you a formula for that. All right, so you've learned the main concepts in this chapter. Okay? Now we'll do a few applications. Okay, so you have a solenoid, and now if you fit, so the inductance of this coil was given by that. Okay, oftentimes you want to increase this inductance. Okay, and to increase this inductance, all you have to do is pack it with magnetic material. And you can find materials easily enough where you can increase the inductance by a factor of 100. Okay? So if you pack it with magnetic material, okay, mu naught gets replaced by mu m, and the inductance can be increased substantially. If a ferromagnetic material is placed inside the solenoid, its inductance can be increased considerably. Okay. So what is an inductor? What is the calling card of an inductor?
It resists change in current.
Very good. Okay, that's what it does. Okay. All right, so now let's look at its application. Now so anytime you learn about a new electrical equipment, what is it that you do? You throw it in a circuit and see how the circuit behaves. Okay, that's how you learn about it. All right. Go ahead. You want to say something? Go ahead.
It's just throwing something that you don't know how it will behave in a circuit doesn't sound like a safe plan.
Well, as long as you don't pass too large a current and stuff like that, it should be good. All right, so we want to learn the behavior of this fella. Yeah. Now, without this fella, so for this circuit, see, we know the behavior of this guy. There's the resistor, the voltage, and current time. Okay, so the behavior of this guy is known. Okay, when you close the switch, when the switch is open, what is the current through this guy?
0.
0. Okay, so we'll close the switch at time t equal to 0, and we'll see what happens. So the current will be, it's 0 before time t equal to 0, and when you close the switch at time t equal to 0, the current rises instantaneously to the value. No. Okay, almost instantaneously, but for our purposes, it's instantaneous. Okay, and what is this current equal to?
Voltage divided by resistance.
Mm-hmm. Okay. Now, we're going to introduce this element in that circuit, and let's see how the behavior changes. That's what we're interested in. So what we're going to do is we're going to ask I, and we're going to close the switch at t equal to 0, and we'll see what happens. And you'll learn, so this is what we're going to show you. The current is going to rise exponentially. Again, the final value will be V over R, except that, remember, this guy doesn't like changes in current. So as the current is trying to go from 0 to its maximum value, this guy is fighting it. But he can only fight so long. Okay, so he slows down the rise of the current. So that's what's happening. Okay. So right now we're starting off slow. See, we're treating him to a DC voltage. So you'll fight for a little while, and then the current will go steady. This is an ideal inductor. He just have inductance. He doesn't have any resistance to it. Okay. So, but any length of wire will have resistance, but we're ignoring that. Okay. So this was what will happen. Next chapter, what we'll do is we'll put him through the paces. We'll attach him to an AC source. Okay? All right. So this is what we want to study. Okay, so what we want to do is we want to study the behavior of this circuit. I've already given you the answer, but we want to study the behavior of this circuit. We want to close the switch and study what happens. Study the development of that circuit. Okay? What is it that's changing? Current will change as a function of time. So we want to study this dynamic behavior of this system. Now, you guys are all differential equation experts. So that's the first thing you do. What do? You see a system, and you come up with a mathematical model for the system. Why do you do that? Because then you don't have to get your hands dirty. You know, setting up stuff in lab is expensive. How do you come up with a mathematical model? To cook something, you need ingredients. You put a physics principle. Okay. So what is the physics principle you're going to put? Well, you close this guy. This is a closed loop. Does anybody have anything to say about a closed loop? That's right. Mr. Kirchhoff tells us that the sum of the voltage changes across all elements in a closed loop will add up to 0. Okay, that's the physical principle that's going to give you the equation. All right, so we close the loop. Let's start here. We'll go across this, plus C. I times our current is flowing from a high voltage to low voltage, so when you go across like that, minus IR. And I is dependent on time there. And then, remember, this guy induces a voltage when the current is changing. And that's the voltage he induces. Minus L di by dt equal to 0. So there is your mathematical model. There is your differential equation describing the behavior of the system. What is it that you're interested in? Define I as a function of time. And so just solve this differential equation. Okay. Easy peasy. Okay, again, system, physical principle gets you the mathematical model. All right, here is the solution to this differential equation. Okay, so the current rises exponentially. Okay, and the time constant of the circuit is L over R. Greater the L value, slower the rise in the current. And that makes sense. What did L do? It was fighting currents, changes in currents, and greater the L value, slower the rise in current. Okay. As for t equal to infinity, this goes to 0, and the current becomes E over R. The steady state value is E over R, just like for the previous circuit. Just like for the circuit without R. Yeah. All right, so now you guys are friendly with this guy. You know the behavior of this guy in a circuit like this. Yeah. All right, so current in an RL circuit, this is called an RL circuit because it has an R resistor and an inductor. Current in an RL circuit builds up exponentially. Yeah. Okay, so you guys remember we close the switch, what happens?
Current starts to flow and
you charge the capacitor. Let's charge the capacitor and then we'll open the switch. Okay? So when you open the switch, you're disconnecting the battery. But remember, the capacitor has energy stored in it. Okay? And you can use that energy. It doesn't store a whole bunch of energy, but you can store the energy and take a picture. You can start a heart. You can use it in a pacemaker and all that stuff. Okay? We'll do the same thing here. So the capacitor stored energy in the form of electric field. It turns out that this guy stores energy in the form of magnetic fields. Okay? This capacitor was able to drive current through this thing. How long did the capacitor drive a current through that flash lamp?
Almost instantly.
Milliseconds. Okay? So same thing. Okay? You can drive a current through this. So what we'll do is we'll take this when the switch is in that position. There's current passing through here. And then when we flip the switch from there to there, what has happened? We've removed the battery. And you'll see that the energy stored in this inductor will pass a current through this for a little bit. Okay. So this device is capable of storing energy. Okay. All right, so what we've done is we've flipped the switch from there to there. And now this is our loop. Okay. And here's the differential equation for the loop. Okay. So here's our system. We put in a physics principle, same Kirchhoff's rule, and came up with this differential equation. Okay. So I'm going to show you a different form of this equation. This circuit here. All right, so here is the battery, here's the inductor, here is the resistor. When this switch is closed, the current flows like that. And then, so we have established a steady state current. And then what we're going to do is, after we've established the maximum current, we're going to open this switch and close this switch simultaneously. We're going to open this. By opening this, you're removing the battery. And by closing the switch, you have this circuit now. Okay, so when this switch was closed, the current was flowing like this. This was a steady current. And then we're opening the switch, closing that. And what will happen is, see, this current is trying to decrease when you remove the battery, but this guy will try and maintain that current. And you'll maintain that current in the same direction. And now we want to see the behavior of this current. We want to get the functional form of this current. This current, again, will last milliseconds. Okay? Because, again, these devices cannot store a whole bunch of energy. You can't cook your pizza with them. All right, so this is the behavior. We want this guy. Okay. Again, what are we going to do? So here's our system. There's our system. Physical principle. Mathematical model. Okay. So what we're going to do is start here, go around the loop, and come back here. Okay. So. What is happening to the current? Is it increasing or decreasing?
Decreasing.
Decreasing. Okay. So the voltage across this is L di by dt. L di by dt. Except that the current is decreasing. So since you're going from low to high voltage, you want a positive. So this is minus L di by dt. Okay. And then you're going from high to low, so minus IR equal to 0. So there is your mathematical model, and you just multiply that by -1 and you get your equation. Okay. So your differential equation, the behavior of this guy is given by I R plus L di by dt. Okay, so this differential equation tells you how this current changes. Yep. And the solution is it's an exponential decay. The current falls off exponentially. Again, the time constant is L over R. Greater the value of L, longer the current will last. Yep. All right, so now what we're going to show you is the following. How did then capacitors store energy?
As in the electric field?
In electric fields. These guys store energy in magnetic fields. Okay? So an inductor resists an EMF source from establishing an instantaneous maximum current in the RL circuit. The battery does work to establish a steady current. And so for instance, if I want to raise this cup, I have to do work against gravity. Okay? So by doing work, I've stored gravitational potential energy. So just like that, if the battery has to do work in establishing a current, it is storing energy. Okay? And in the process, it stores energy in the inductor. Okay? So again, we're going to close the circuit, close the switch, and so for this closed loop, there's the differential equation. We already did that last time. Okay? And now all we're going to do is multiply this by I. So multiply that by I. Bring these terms to the other side, and you get I squared over R. I squared times R, and L I di by dt. What is this fella?
Power?
Yeah, that's the rate at which this guy is providing power. This is equal to the rate at which this guy is providing power. What is this guy? That's the rate at which this guy is receiving power, and he's doing whatever. Maybe he's cooking pizza, lighting a bulb, or whatnot. That's the rate at which that guy is using that energy. And this guy can be written like so. So this is the rate at which this power is dissipated here. And it turns out that this is the rate at which energy is being stored here. Okay, so this can be your earnings, this can be your rate of spending, and this is the rate of your savings. So the energy stored in an inductor when a current I flows through it is that. Yeah. All right, so the rate at which energy is stored is du by, okay, so this is the energy stored in the inductor. When the current is zero, how much energy is stored in the inductor? Zero, because there's no magnetic field in there. Yeah. All right, so now we'll show you that. Okay. So anytime you have a current flowing in an inductor, it creates a magnetic field. And ideally, in the ideal case, the magnetic field is all inside, and outside it falls off rapidly to zero. Okay, so the magnetic field is. So we'll imagine an infinitely long inductor, and then all the magnetic field is inside. Okay. All right. So the energy stored in the inductor is 1/2 Li square. L is given by that, and the magnetic field inside a solenoid is given by that. So if you substitute that, so okay, so what we're going to do is U is 1/2 L, L is mu naught N square AL, and I is B over mu naught N square. Okay. So if you simplify all of this, the energy turns out to be this times AL. A is the area of cross section, and L is the length of the inductor. That's the volume of the inductor. That's the volume of the solenoid. So The energy stored is the energy density times the volume of the solenoid. Okay, so this is the energy stored per unit volume in the magnetic field. Okay. So this guy stores energy in the magnetic field. Okay. So the next application we'll look at is transformers. Okay. Do transformers work with DC current?
Only once?
No, yeah, yeah, only very small time. Yeah. So they don't work for DC current. Okay. So you apply AC current, you're switching the magnetic field here, and the changing magnetic field induces a voltage here. The output voltage is N2 by N1 times the input voltage. Okay. N2 greater than N1 is a step-up transformer, and N2 less than N1 is a step-down transformer. All right, so now you're learning something very interesting, something that you probably don't realize, but you're using many of these guys in your life all the time. So let me start off with an analogy. Okay, so this is the equilibrium position of this mass attached to a spring. And what I'll do is I'll pull this mass to the right and let go. What will happen? How long?
Oscillates back and forth.
Huh?
It oscillates back and forth.
How long?
Until the friction cancels the movement.
Yeah, so if there's no friction,
Forever.
forever. Okay? And at what frequency does it oscillate? So the frequency depends on the spring constant and the mass attached. Okay, so frequency is 2 pi, 1 over 2 pi. Okay, I'm not sure of the K over N. See, the frequency is characteristic of this system. Yep. Stiffer the spring, more times it'll oscillate. Heavier the mass, fewer times it'll oscillate per second. All right, we'll do the following. We'll take a capacitor and an inductor. Okay. By the way, so for this to oscillate, for any system to oscillate, what is needed? What's special about this thing that it oscillates?
Two differences in potential.
I'm sorry?
Two differences in potential.
It needs energies in two different forms. This has spring potential energy and kinetic energy. And whenever a system is oscillating, all that is happening is energy is being converted from one form to another. Okay? You can have more than two different forms of energy and you can oscillate too. But that's what's needed. Okay? So for a system to oscillate, it has to be able to have energy in two different forms, and all that when it's oscillating, it's converting energy from one form to another. All right, so let's use this device. Okay, do we have the basic ingredients? This guy stores energy in electric fields. This guy stores energy in magnetic fields. So we have the ingredients. Okay? And this guy oscillates. Okay, so we charge the capacitor and let go. Okay. This capacitor will drive a current like that. Okay, and start storing energy in magnetic fields. All the energy gets transferred here into magnetic fields, and now this guy will start driving a current and transfers this energy back to the capacitor. Energy is in the capacitor, and now this guy will drive current like that. Okay. Energy is back there, and this guy will start energy. Okay, so you see the circuit oscillates. Okay, back and forth. how long will this oscillate?
Forever.
Forever. If there's no resistance in the circuit, resistance is the parallel of friction. So if there's no resistance in the circuit, the electrical energy is not being dissipated into heat. Okay, that's what friction does. Friction removes mechanical energy to heat. Okay, so this will oscillate forever. Okay, just like this had a frequency dependent on the system parameters, this has an oscillation frequency as well. Okay, and the oscillation frequency, omega, which is 2 pi f, is equal to 1 over square root of LC. And this device is magical. All right, so let's see what's magical about this. Okay. So here's its natural frequency. Okay. Do you guys know what is resonance? Okay, what is resonance?
You can increase the amplitude by matching that frequency.
So if you have a driver whose frequency matches the natural frequency, you can set up large amplitude oscillations. Okay, so here's what we're going to do. Yeah, so we're going to use this device. So, oops. We've given it rabbit ears just to be able to talk outside. So this guy has a frequency. Okay. And what we'll do is fill this room with electromagnetic signals. F1, F2, F3, F4. Okay, so these are all different frequencies. Okay. The frequency that matches the natural frequency of this will drive a large current in the circuit. Any other frequency won't talk to him too much. Okay, they won't set up large amplitude currents. The frequency that matches this natural frequency will set up a large amplitude current. So that's how you pick up the signal that you want. So this room is full of all kinds of radio signals. How do you pick up the signal frequency you want? You change the values and tune this to the frequency you want to pick up. Okay? And then you get a large amplitude signal, and then you can process that signal. So this is at the heart of all tuning devices. This is a tuner. This is at the heart of all wireless devices. Okay? And this can be a transmitter as well. So, a wireless device, when it transmits a signal, this is the antenna. So, so again, we are all experts at differential equations. So as soon as you see a system, you set up a mathematical equation and then solve for it. Okay. So here's our system. Again, you'll use Kirchhoff's, well, no, not Kirchhoff's law this time. The energy stored in this guy is that. The energy stored in this guy is that. Okay, so if there's no resistance, there's no friction, what is happening to the total energy? The total energy remains constant, so d by dt of that is 0. Okay, and so you get this differential equation for the charge on the capacitor. Okay, and you can solve this differential equation, and the charge on the capacitor oscillates with that frequency, which is the natural frequency of oscillation. Okay? And the current also oscillates with that frequency. Okay, so the natural frequency of the system is omega is 1 over square root of LC. Okay. So here's how you talk to this guy. So here's this basic tuning circuit. Here's the variable capacitor. Why is the capacitor variable? So you can change the frequency of this guy. Okay, so pick up whatever frequency you want to pick up. Okay, and unfortunately, all devices, we don't have frictionless devices, so they'll have some resistance. Here's the inductor. Okay, and here are rabbit ears to talk to the outside world. There's the antennas. Okay, so if this frequency matches the natural frequency of this guy, he'll set up a large amplitude oscillation. Okay. And then, if you place another inductor coil here, you can transfer the information from here to there and then process it in your black box. Yeah. So, that's how radios work. All right, so now we'll analyze this circuit. Okay, without this present, this guy would oscillate forever. With this guy present, this guy, what is he doing? What is this guy doing?
Dissipating energy.
Yeah, it's converting electrical energy to heat. Okay. Right, so here's a mechanical parallel of it. So if you had just a mass in the spring, it would oscillate forever, no friction. You put it in a beaker full of liquid, that'll provide resistance, and that energy will dissipate. Okay, so here's a simple way of getting the differential equation for this system. Okay, here's the total energy stored in these two guys, and this fellow is dissipating. So the rate at which this energy is decreasing, the electrical energy is decreasing, is equal to the rate at which this guy is dissipating energy. Okay, and so here is the differential equation for Q. Okay. Now you see this differential equation is very similar to the differential equation for this guy. Mass times d square x by dt square equal to minus kx minus b dx by dt. That's the differential equation for this guy. I'm going to bring this over there. M d square x by dt square plus b dx by dt plus kx equal to 0. So you see the differential equation for this, the charge on the capacitor and the position of this guy are very similar. Okay, the mass is taken, the mass is replaced by L, B is replaced by R, K is replaced by 1 over C. The exact same differential equation. So here's the amazing part. See why you learn differential equations. These are two very different systems. They're governed by the same differential equation. Yeah. And so you learn to solve one, you know the solution to another one, to the other one. Okay? So the charge on the capacitor decays exponentially. Okay? And the frequency of oscillation of this system is slightly different than the frequency of oscillation of this, just that system without the resistance. See, the frequency of oscillation changes ever so slightly. Well, depends on the value of R. Smaller R is, smaller the change in frequency. For R such that this is 0, then the system won't even oscillate. That's the critical value of R. Okay? All right, so you saw that these two systems, even though they look very different, they're governed by the same differential equation. Okay. All right, guys, so that finishes this chapter.